Color blindness affects a person's ability to perceive colors and can contribute to difficulties in everyday life and at work. All types of color blindness involve difficulties distinguishing, recognizing, and especially comparing colors, like when matching clothing. HaptiColor is a wristband that gives haptic feedback by means of spatiotemporal vibrotactile encodings. The encodings can translate any kind of data, helping a user understand the spatial relationships among multiple points on a line or a circle. When mapped to a color wheel, HaptiColor's vibration patterns can help colorblind users understand the relative relationship between colors. In our study, we empirically validated both the encodings and the prototype. We first had to determine the ideal number and position of vibration motors. The band of motors begins with M1 placed 35 mm up from the center of the wrist bone on the dominant hand. We then tested how accurately users could locate the vibrations around their wrist, how fast they could respond to a stimulus, and how difficult they felt this task was. Our participants felt 3 motors was the easiest and most accurate, with around 95% accuracy and 2 seconds response time. 4 motors was the next most accurate configuration, but 5 motors was seen as more difficult with a corresponding drop in accuracy and response, while 6 motors was especially hard, seeing a response time of 3 seconds and a much lower accuracy. We chose 3 motors for our prototype, not only for users' preferences, but also because it maps well onto the 3 primary colors, in our case red, green, and blue. There are 12 total colors in this color wheel, so we must make an encoding to represent these 12 colors using only 3 motors. We accomplish this by manipulating 3 dimensions of vibration with the motor at high, low, or idle levels. This gives us 3 sets to communicate information: duration, pulse, and intensity. Patterns within each set can be played simultaneously or sequentially. In the case they are played sequentially, the motors are activated clockwise with a 200 millisecond pause between vibrations. Simultaneous patterns were faster but made information harder to perceive, leading us to choose sequential patterns. Remember, we must represent 12 points or colors with 3 motors. The patterns were thus designed to represent interpolated points, points not located directly on a physical vibration motor, but also in an imaginary space in between. Let's focus on 2 vibration motors covering red through green. Red would be encoded by expressing a strong value on the first motor and a value of none on the second. Orange would then be represented as a strong value on motor 1 and a medium value on motor 2. This pairing of strong and medium values suggests this color is closer to the second motor than the first. Yellow, a point directly in between motor 1 and 2, is encoded by a medium value on each motor, and so on. Using this prototype and our encodings, we tested the ecological validity of HaptiColor with colorblind participants in a within-subjects experiment. They could easily locate and interpret the vibrations, achieving a color matching accuracy of between 94 and 100%, reporting a greater sense of confidence when matching colors compared to their own vision. A future version could employ an embedded color sensor providing real-time information in everyday settings.